More than 1,000 people died because someone decided the building was finished. It wasn't. That single case, which you'll find at the top of this list, is enough to reframe everything you think you know about construction failures. Because the most dangerous moment in architecture isn't the earthquake, the flood, or the fire. It's the meeting where someone says the budget is tight and nobody pushes back. Today, we're counting down 13 structures where the gap between intention and reality turned catastrophic. Not because of natural disasters, not because of malice, because of overconfidence, skipped steps, and the very human tendency to assume that someone else already checked the thing that nobody actually checked. The list includes a skyscraper where the designers simply forgot to plan elevators for the upper floors, a bridge that survived a hurricane in perfect condition, but became completely useless after the river shifted course and left it stranded over dry land. A hotel facade that functioned as a parabolic mirror, focusing sunlight into a beam hot enough to melt plastic and burn guests by the pool. A tower in Manhattan that came within hours of collapse, a story so quietly buried that most engineers only learned about it decades later. And that building, the one where more than 1,000 people were killed, not by a storm, not by an explosion, but by flaws that were never strong enough to hold the weight placed on them. This isn't a disaster countdown for entertainment, it's a forensic look at how human error operates at the scale of concrete and glass. Each of these 13 stories follows the same arc, a promise made on paper, a compromise made in practice, and a reckoning that nobody saw coming. Stay with us. 13 will surprise you. 1 will stay with you. 13 floors from the top of a luxury skyscraper, the elevators simply stopped. Not because of a malfunction, not because of a power cut, but because the shafts had never been built that far up. That is the defining absurdity at the heart of the Intempo Tower in Benidorm, Spain, number 13 on our list, and one of the most astonishing engineering oversights in modern construction history. Benidorm sits on the Mediterranean coast of the province of Alicante, and by the early 2000s it had earned an unlikely nickname, the Manhattan of the Sea. Dozens of high-rise residential towers packed tightly along the beachfront had given the resort town a skyline that looked borrowed from a much larger city. It was in this atmosphere of relentless vertical ambition that construction on the Intempo skyscraper began in 2006. The original plan called for a building of considerably more modest proportions. Then, midway through construction, with the foundations already poured and the lower floors already rising, the developers made a dramatic decision to nearly double the building's height, pushing it to 47 stories and positioning it as one of the tallest residential structures in the country. Redesigning a building mid-construction is never simple. Every load calculation, every structural element, every system running through the building has to be reconsidered from scratch. And somewhere in that frantic process of revision, something fundamental slipped through the cracks. The updated plans failed to include elevator shafts for the upper floors. The mechanical infrastructure was locked into the original, shorter design. As a result, residents on the higher floors would have faced no choice but to climb. The financial crisis of 2008 arrived before the full scale of the problem could even be confronted, freezing construction entirely and leaving the unfinished concrete frame standing for nearly a decade, a monument to overreach visible from the beach. Multiple contractors came and went, legal disputes dragged on through the courts. It was only in 2020 that Intempo was finally completed and partially occupied, more than 14 years after the first shovel broke ground. The tower that was meant to crown Benidorm's skyline instead became its cautionary tale, proof that in the race to build higher, the details that make a building actually livable can vanish entirely. No lives were lost here, but the cases ahead on our list will show just how steep the price of an overlooked detail can become. The bridge was perfect, structurally flawless, not a single crack, every load-bearing calculation vindicated by the storm that destroyed nearly everything around it, and it was completely useless. That is the story of the Choluteca Bridge in Honduras, ranked 12th among the most instructive design failures in modern history. Not because it collapsed, but precisely because it didn't. In 1998, Hurricane Mitch struck Central America with a ferocity the region had never recorded. Honduras bore the worst of it. More than 600 millimeters of rain fell within days. Rivers burst their banks. Entire villages vanished under mud and floodwater. Thousands of people died. Roads, dams, and bridges across the country were obliterated. The destruction was so thorough, it set Honduran infrastructure back by decades. Among the wreckage, one structure held. The bridge over the Choluteca River, built with Japanese financial support and completed shortly before the disaster, came through the hurricane without damage. Engineers had designed it to withstand extreme flooding events, and it did exactly that. By every conventional measure, it was an engineering triumph. Then the water receded, and the triumph revealed its limits. The Choluteca River, over the course of the storm, had carved itself an entirely new channel. It had simply moved, scouring through the softened banks and abandoning its historical bed. When the floodwaters finally drained away, the bridge stood over dry ground. Its approach roads had been swept away. It connected two banks of a river that no longer flowed beneath it, a crossing to nowhere. The reason this happened lies in what the engineers were never asked to consider. The design brief assumed a fixed geography, a specific river in a specific location. The calculations accounted for the river's force, but not for its mobility. No model included the possibility that the waterway itself might relocate. The structure was optimized for a world that the hurricane erased and replaced with a different one. This is why the Choluteca Bridge has entered engineering and business curricula worldwide as the canonical example of what theorists call solving the wrong problem correctly. The execution was beyond reproach. The underlying assumption was catastrophically wrong. And that distinction matters enormously, because a flawed assumption embedded in a brilliant solution is far harder to detect than an obvious structural weakness. The bridge warns us that in conditions of rapid, non-linear change, the most dangerous failure is not the one that breaks under pressure. It is the one that stands perfectly intact while the world shifts around it. A 57-story glass tower in the middle of the Mojave Desert was turning people's hair into kindling, not metaphorically. Guests lounging by the pool at the Vdara Hotel in Las Vegas were reporting scorched scalps, melted plastic cups, and a concentrated beam of heat that appeared without warning in specific spots around the pool deck. Staff had a name for it: the death ray. This is number 11 on our list. To understand how a luxury hotel became a solar weapon, you need to think about geometry. The Vdara's facade curves inward slightly, a concave design chosen for purely aesthetic reasons, meant to give the building an elegant silhouette and help it flow visually within the broader city centre complex. It looks beautiful. It also behaves exactly like a parabolic mirror. Thousands of glass panels arranged across a concave surface collect reflected sunlight and focus it into a single concentrated point, the same principle behind a telescope mirror or a satellite dish, just running in reverse. That focal point happened to land on the hotel's pool area. Calculations carried out after guests started complaining put the temperature at the focus at around 65 degrees Celsius, enough to cause skin burns within seconds of exposure. Las Vegas already sits in one of North America's most punishing climates, with summer air temperatures regularly exceeding 40 degrees and nearly 300 cloudless days per year. The building was essentially amplifying an already extreme environment and directing the result at the people who had paid to relax there. What makes the Vdara case particularly striking is the timeline. The building went through design review, permitting, construction, and grand opening without a single engineer or architect catching the effect. No simulation flagged it. No inspection revealed it. The problem was discovered the old-fashioned way. Guests complained. Management's solution was equally low-tech. Shade canopies stretched over the worst affected zones, and a handful of trees planted for additional cover. A multi-million-dollar architectural miscalculation corrected with canvas and saplings. No one died. Hair was singed, plastic melted, and the reputations of several designers took a quiet hit. But the consequences remained cosmetic, which is more than can be said for the structure we turn to next, one where a similar failure to anticipate basic physical forces turned an ordinary windy afternoon in an English city into something far more dangerous. A perfectly ordinary gust of wind killed a man in Leeds. Not a storm, not a hurricane. Meteorologists recorded nothing unusual that March day in 2011. The wind was moderate, entirely typical for the north of England. And yet a lorry was flipped onto a pedestrian at the base of Bridgewater Place, and he died. The building didn't just fail to protect him, the building created the force that killed him. Bridgewater Place sits at number 10 on our list. Standing 32 stories tall, it's the highest structure in Yorkshire, completed in 2005 to designs by the architectural firm ADAS. On paper and in photographs, it looks like exactly what a modern city centre skyscraper should be. Mixed use, sleek, ambitious. Offices in the upper floors, apartments, restaurants at street level. A polished rectangular tower with smooth glass facades rising above the heart of the city. That smooth rectangular form is precisely the problem. When the prevailing westerly wind strikes the broad, flat face of the building, it has nowhere to go horizontally. Physics forces it downward. It pours into the narrow streets at the tower's base and accelerates dramatically. Engineers describe this as a combination of the Venturi effect and a downwash vortex, two mechanisms that work together to compress and speed up airflow at ground level. The result is that wind speeds on the pavement below can be several times higher than the wind speed measured at elevation. The building acts like a funnel, concentrating atmospheric energy at exactly the point where human beings are most vulnerable. This is what happened in March 2011. Ordinary weather, extraordinary violence. A lorry overturned, a man died, and the aftermath was almost as troubling as the event itself. Leeds City Council was forced to close surrounding streets to heavy vehicles on windy days, a restriction that remained in place for years. Legal and regulatory arguments dragged on about who bore responsibility: the developer, the designers, or the city planners who approved the scheme without requiring adequate wind analysis. That last point matters most. At the time Bridgewater Place was approved, pedestrian-level aerodynamic modelling was not a mandatory part of the planning process for tall buildings in urban environments. Nobody was required to simulate what that tower would do to the air around its base. The gap in regulation cost a man his life. Bridgewater Place still stands. It is still beautiful, and on a windy day, it is still dangerous. But if this building turned wind into a weapon, the next entry on our list achieved something equally extraordinary. It turned sunlight into one. Nearly 100 skyscrapers are slowly falling over in the same city, and the authorities have decided to simply let them lean. That is not a thought experiment. That is Santos, Brazil, number 9 on our list, a port city on the Atlantic coast of São Paulo state, and arguably the most spectacular concentration of geotechnical failure anywhere on the planet. The paradox is this: the very thing that made Santos desirable is the same thing that made it structurally treacherous. In the mid-20th century, wealthy Brazilians craved seafront apartments, and developers were only too happy to oblige. Tower after reinforced concrete tower rose along the waterfront, each one a monument to ambition and, as it turned out, to a catastrophic lack of geological curiosity. Nobody looked beneath the surface. If they had, they would have found a thick layer of soft marine clay hiding just below the thin crust of urban soil, a material so weak and compressible that it behaves less like ground and more like a slow-motion liquid under sustained load. Foundations were laid shallow and without proper site investigation. The clay did what clay does. It yielded. The buildings began to sink and tilt, almost imperceptibly at first, then undeniably. Today, the Santos skyline, viewed from the waterfront, looks like a row of exhausted soldiers leaning away from one another, each tower tilting in its own unique direction, depending on exactly where the softest clay happened to sit beneath its footprint. Inside these buildings, residents have long since made peace with sloping floors and doors that jam in their frames. One structure has drifted more than a metre from true vertical. Demolition and mass evacuation remain politically and logistically unthinkable, given the sheer scale of the problem and the number of families still living inside. Santos has become an open-air textbook, a permanent warning about what happens when construction ambition outruns engineering discipline. But if Santos tilts in slow silence, our number 8 entry did the opposite. It shed glass onto Boston pedestrians with dramatic and deafening urgency. That story belongs to the John Hancock Tower. The most expensive window replacement in history was caused by a thin strip of lead. That is the core of what went wrong at the John Hancock Tower in Boston. And it took the city years, thousands of panels, and a bill that exceeded the original glazing contract to fix it. The tower was supposed to be a triumph. 60 stories of blue reflective glass rising over Copley Square, its mirrored surface catching the sky and bouncing back the Gothic silhouette of Trinity Church next door. Designed by the firm of Pay, Cobb and Freed, the building was meant to define American modernism in steel and light. Instead, it defines something else entirely: what happens when a material fails at scale. Before the building even opened, the double-pane glass panels began to crack and fall. Each unit measured nearly 1.5 square meters. In 1982, pedestrians on Clarendon Street would sometimes hear a sudden crack above them, look up, and watch a panel detach from 60 floors up, rotating slowly through the air before detonating on the pavement below. The sound carried a full city block. The surrounding streets were closed periodically as a precautionary measure, and Boston learned to give the building a wide berth. Engineers traced the failure to the lead interlayer bonded between the two panes of glass. Under cycles of temperature change and wind pressure, the lead deformed. Once it deformed, the seal broke. Once the seal broke, the panel had nothing reliable holding it in place. The fix for individual panels was plywood. More than 300 openings were boarded up with dark wooden sheets while the investigation continued, leaving the gleaming modernist tower looking like a patched-up warehouse. Bostonians called it the most expensive wooden skyscraper in the world, and the name stuck. The permanent solution was total. All 10,344 glass panels were removed and replaced with a corrected design. Every single one, regardless of whether they had failed yet. The cost of the repair exceeded the cost of the original installation. The John Hancock Tower ranks 8th on our list of architecture's most consequential and costly failures. Glass, at least, announces its failure loudly. The next case on this list involves a structural error buried inside the bones of a skyscraper, silent and invisible, until a student's question during a university seminar forced an engineer to do the calculation he had never done before. 1 million litres of seawater does not leak, it detonates. That is the only word that makes sense when you consider what happened inside the Radisson Blu Hotel in Berlin at 4 a.m. on a December night in 2022. Number 7 on our list is the Aquedom, and its story is a masterclass in how catastrophic failure hides in plain sight for years before announcing itself without warning. The Aquedom had been a fixture of the hotel lobby since 2004. 16 meters tall, roughly 11 meters across, it held 1 million liters of saltwater, 1,500 fish, and a glass elevator that carried tourists up through the water column as though gravity had simply been suspended for their amusement. It was the largest cylindrical aquarium in the world, and for nearly 2 decades it was treated as an architectural given, something permanent, something safe, something beyond question. Then the acrylic wall gave way. The water did not spill. It erupted outward in seconds, tore through the lobby interior, blew out the glass entrance doors, and flooded the surrounding streets. 2 guests were injured by flying debris. Almost every fish perished. The building was condemned. Investigators found no explosion, no external force, no single catastrophic mistake. What they found instead was material fatigue. Microscopic cracks that had been accumulating inside the acrylic for years, likely accelerated by the sharp temperature swings of that particular Berlin winter. The structure had been failing incrementally, invisibly, for a very long time. Nobody noticed because nobody thought there was anything to notice. That is precisely the point. The Aquedom did not collapse because of what happened to it. It collapsed because of what had been quietly happening inside it all along. The only reason this story does not end with fatalities is chance. Pure, uncomfortable chance. Up next, a skyscraper in the heart of Manhattan that nearly killed thousands, and the engineering student who almost stopped it alone. Number 6 on our list is a story that almost erased 10 city blocks from the map of Manhattan, and the only reason it didn't is because one man chose honesty over self-preservation. The Citycorp Center Tower was completed in 1977, 59 floors, an instantly iconic silhouette, and a structural concept unlike anything else on the New York skyline. The building didn't rest on corner columns. Its 4 massive stilts were planted at the midpoints of each side, an arrangement forced, of all things, by a small Lutheran church that occupied the corner of the site and had to be preserved. The result looked breathtaking. It also contained a flaw that nobody caught until it was almost too late. In 1978, an architecture student named Diane Hartley asked Chief Structural Engineer William LeMessurier a straightforward question about load calculations on the building's joints. LeMessurier went back to his numbers. What he found there must have felt like the floor dropping out beneath him. During construction, the contractor had quietly substituted bolted connections for the original welded joints on the diagonal bracing. A cost-cutting decision made without proper authorization. On paper, the change seemed minor. In reality, it had dramatically weakened the tower's resistance to quartering winds, gusts striking the building at its corners rather than its faces. LeMessurier calculated that a storm of moderate intensity, the kind New York sees roughly once every 16 years, could bring the entire structure down. He told the authorities anyway. For 3 months, from August through November of 1978, repair crews worked exclusively at night, welding steel plates over the compromised connections, while office workers filled the building by day and the surrounding neighborhood went about its life, completely unaware. City officials quietly drafted an emergency evacuation plan covering 10 blocks in every direction, ready to move if the hurricane season arrived before the repairs were finished. The story stayed buried for nearly 20 years. It was journalist Joe Morgenstern who finally brought it into the open in a 1995 piece for The New Yorker. By then, the building was safe. LeMessurier's reputation, rather than being destroyed, was largely regarded by his peers as a case study in professional integrity. The engineer who found the mistake and fixed it, instead of hoping no one else would. The tower still stands. But if Citycorp Center was saved by a single act of courage, our next entry shows what happens when the warnings go unheeded and the costs are measured not in emergency repairs, but in something far harder to recover. Number 5. The Montreal Olympic Stadium. The roof was supposed to be the miracle. it turned out to be the wound that never healed. Montreal's Olympic Stadium ranks 5th on our list, and its story is one of the most expensive lessons in the history of public architecture. A project where every solution created a bigger problem than the one it was meant to fix. When the city won the right to host the 1976 Summer Olympics, architect Roger Talibert unveiled a vision that stunned the engineering world. A stadium crowned by a tilting tower standing approximately 175 meters tall, from which a retractable roof made of Kevlar fabric would be suspended. Kevlar at the time was the stuff of aerospace dreams, lightweight, extraordinarily strong, almost futuristic. On paper, the design was a genuine leap forward. In practice, it became a slow-motion catastrophe. The roof wasn't finished in time for the opening ceremony. Athletes competed under open skies, while officials promised delays were temporary. When the Kevlar canopy was eventually installed, it began to tear. Then it tore again. In 1991, a section collapsed into the stadium bowl. In 1999, history repeated itself. Repair crews came and went, each visit costing millions more. Eventually, the retractable concept was scrapped entirely in favor of a fixed roof, which brought its own separate catalogue of failures. The financial picture is where the story becomes almost surreal. The original construction budget was approximately $124 million. By the time decades of repairs, overruns, and maintenance costs were tallied, the total had exceeded $5 billion. To service that debt, Quebec authorities introduced a dedicated tobacco tax. The residents of Montreal paid it for nearly 30 years. The final payment was made in 2006, 30 years after the Olympic flame was extinguished. Locals gave the stadium a nickname that captured everything: the Big O, a bitter twist on its official name, the Big O. The tilted tower still leans over the city skyline today, visually magnetic and quietly accusatory. It is a monument to the gap between what ambition promises and what reality delivers. But if Montreal's failure was measured in dollars, what comes next is measured in something far more precious. 59 floors above Midtown Manhattan, a skyscraper was quietly preparing to fall, and almost no one knew. Number 4 on our list. A building can kill you, not because it was poorly maintained, not because it was old, and not because anyone made a single dramatic mistake, but simply because it was built cheap. That is the brutal lesson of the Versailles wedding hall collapse in Jerusalem in May 2001. Nearly 700 guests had gathered on the 3rd floor of the banquet venue to celebrate a wedding. The music was loud, the dancing was vigorous, and the floor was doing exactly what floors are supposed to do, holding everyone up. Until it wasn't. Without warning, the entire 3rd floor slab gave way. It collapsed downward, pulling tables, columns, and people into the void below. 23 people were killed. Close to 400 were injured. The investigation that followed uncovered not an accident, but a system, a construction method called pal-cal, developed in Israel as a cost-cutting approach to building. Pal-cal floors were made from lightweight hollow-core blocks with minimal steel reinforcement. The method was widely used across commercial construction because it was cheap and fast. What was rarely said out loud was this: those floors were never engineered to handle dynamic loads. Static weight, furniture, people standing still, was manageable. But hundreds of bodies moving in rhythm, generating synchronized vibration, created forces the structure simply could not absorb. Using pal-cal in ballrooms, grandstands, or banquet halls was not a calculated risk. It was a structural contradiction. The Versailles disaster forced Israel to confront that contradiction at a national scale. Inspections were ordered across the country. Buildings constructed with pal-cal were reviewed. Some were closed, others were reinforced. Building codes were rewritten. But the 23 people who died at a wedding celebration cannot be written back into the living. The tragedy in Jerusalem showed what happens when economic logic overrides engineering honesty in commercial construction. Our next case shows that ambition and innovation carry their own dangers. even at the highest levels of global architecture. We turn to the Montreal Olympic Stadium. A bridge does not collapse in an instant, it collapses over decades, and the Morandi Bridge in Genoa had been falling for years before anyone admitted it. On the morning of August 14, 2018, a Tuesday, the collapse simply became visible. At 9:36, a 200-metre section of the A10 motorway viaduct gave way. 43 people died. Cars plunged 45 metres onto railway tracks and residential rooftops in the Sampierdarena district below. The bridge had been standing since 1967, designed by Riccardo Morandi, an engineer celebrated in Italy as a master of reinforced concrete. His design for the Genoa viaduct was unconventional. Rather than exposed steel cables, Morandi encased the load-bearing tendons in concrete sheaths. The idea was elegant in theory. The concrete would shield the steel from corrosion. In practice, it created a slow catastrophe. Moisture accumulated inside the casing. Oxygen seeped through hairline cracks. The steel corroded invisibly, inaccessible to standard inspection methods, year after year. Morandi himself raised the alarm in the 1980s, writing that the structure required serious repair. His warnings were filed away. Autostrade per l'Italia, the private company holding the motorway concession, was aware of the deterioration. Independent engineers flagged the structural degradation repeatedly. Repairs were scheduled, postponed, rescheduled. According to investigators, maintenance costs were consistently weighed against the financial interests of the concessionaire and consistently lost. In 2019, Italian prosecutors charged company executives. The word that appeared throughout the case documents was negligence. Not accidental, not isolated, but systemic and years in the making. The neighbourhood beneath the viaduct was partially destroyed. Residents of buildings directly under the bridge were evacuated. A new crossing designed by architect Renzo Piano opened in 2020. Genoa rebuilt its connection across the valley. The 43 victims cannot be rebuilt. This is number 3 in our countdown. Next, how architectural ambition and decades of mismanagement turned a symbol of national pride into an engineering and financial catastrophe half a century in the making. The Olympic Stadium in Montreal, built longer than planned and still being paid for today. Number 2 on our list takes us to California, March of 1928, and to a man who built an empire out of water and will. William Mulholland had no engineering degree. He never attended university. He started as a ditch digger, taught himself hydraulics from borrowed textbooks, and rose to become the architect of Los Angeles' entire water system. His aqueduct from the Owens Valley had already transformed a sun-baked desert town into a city of the future. Mulholland didn't just build infrastructure, he was the infrastructure. His reputation was the blueprint. The St. Francis Dam stood 60 meters tall and held back nearly 47 billion liters of water in the Santa Clara River Valley. It was, by any measure, an extraordinary structure. It was also sitting on a catastrophe that geological surveys had already tried to name. Reports flagged the western bank as conglomerate rock, the kind that softens and dissolves when saturated. The eastern bank was worse, an ancient landslide, barely stable, waiting for the right conditions to move again. Mulholland read those reports. He proceeded anyway. In the hours before midnight on March 12th, the dam's keeper noticed something wrong. Seepage, new and darkening. Mulholland came out personally, looked at the leaks, and called them acceptable. He drove away. The dam failed before dawn, not slowly. The wall simply ceased to exist, and a wave that reached heights of up to 38 meters tore through the valley toward the Pacific, taking houses, farms, and entire communities with it. Somewhere between 400 and 600 people died. The exact number was never fixed. At the inquest, Mulholland said something that has followed his name ever since. "I envy the dead." He never recovered. His career ended that morning in the dark water. What the disaster exposed was larger than one man's confidence. It revealed an entire era's assumption that reputation could substitute for rigor, that intuition built on experience was as good as geological fact. California responded by introducing mandatory state oversight of dam construction for the first time. The ground itself had betrayed the builder. But if the St. Francis collapse was a failure of what lay beneath the structure, the disaster at the top of our list was a failure built into the structure itself, invisible, mathematical, and almost total. It might have been the largest engineering catastrophe in modern history. It wasn't, because a student asked a question nobody wanted to answer. The workers were told to go back. That single decision killed more than 1,000 people. On the morning of April 24, 2013, cracks had already split the walls of Rana Plaza, an 8-story complex on the outskirts of Dhaka, Bangladesh. The bank on the ground floor had seen enough. It evacuated its staff the previous day and did not reopen. But the garment factory owners operating on the upper floors made a different calculation. They threatened workers with dismissal if they refused to return. So they returned. When the industrial generators switched on and sent vibrations through a structure that was never built to carry this load, the building collapsed in seconds. More than 3,000 people were buried under the rubble. 1,134 of them died. This is the deadliest structural failure caused by human negligence in modern history, and it sits at number 1 on this list for a reason. Rana Plaza was not an accident waiting to happen. It was an outcome that had been engineered, step by step, by decisions made long before that morning. The original permit allowed for 5 floors. The owner, Sohail Rana, built 8 using substandard concrete and reinforcement bars that met no recognized safety standard. The foundation sat on waterlogged ground and had never been properly reinforced. Each additional floor was another layer of pressure on a base that could not hold it. What collapsed that day was not just a building. It was the illusion that cheap clothing has no human cost. The workers inside were sewing garments for some of the largest retail brands in Europe and North America. Labels whose customers had no idea their purchases were being assembled under conditions that violated every basic standard of safety and dignity. The disaster forced a reckoning. More than 180 international brands eventually signed the Bangladesh Accord on fire and building safety. But the agreement came after the rubble, not before it. Rana Plaza is first on this list because the scale of the failure was total, structural, managerial, and moral. Before we reach this point in our countdown, we must pass through the story of a dam built by a man who believed he was a genius and who drowned 600 people in a single night. Every single one of them had warnings. That is the most unsettling truth running through all 13 of these stories. Not that disasters happened, but that they were announced in advance and ignored anyway. 13 structures, 13 moments when ambition, calculation, and an unshakable belief in one's own judgment collided with a reality that kept its own schedule. The bill arrived differently each time, sometimes measured in billions of dollars, sometimes in hundreds of lives. Engineer Mulholland dismissed the geologists. The owners of Rana Plaza dismissed the inspectors who had ordered the building evacuated the night before those sewing machines started up on the 8th floor. The operators of the Morandi Bridge in Genoa had their own corrosion reports sitting in their files and kept the bridge open anyway. A skyscraper built without elevators, a dam constructed without geological survey, a bridge that outlasted hurricanes but couldn't survive a river shifting course, a stadium whose roof couldn't protect the people sheltering beneath it, a wedding hall in Jerusalem that came down on its guests. On the surface, these are separate catastrophes from separate countries and separate centuries. Look closer, and the architecture of failure is identical every time. Overconfidence plus cost-cutting plus silence equals tragedy. The pattern is almost mechanical in its consistency, and the people who made the decisions were almost never the ones who paid for them. The workers on the morning shift paid. The drivers crossing a Genoese highway on a wet Tuesday in August paid. The wedding guests paid. Every structure is someone's trust, poured into concrete and steel and left to hold. 13 times that trust collapsed. 13 times the signs were there. 13 times someone in a position to act looked away. The history of engineering is a history of extraordinary human ambition. It is also a precise record of what happens when ambition tips into arrogance. Don't let that trust fall. If this episode made you think, like it, share it with someone who needs to hear it, and subscribe. The next one is already waiting.